Morning, good afternoon, and welcome to all of you joining via Zoom for this recorded lecture of our high performance machine learning class. Today, I'm very delighted to host a special guest lecturer in our class. Please join me in welcoming Dr. Hadjer Benmeziane, an expert in hardware-aware neuroarchitecture search from IBM Research. I also would like to let you know that we will have a live Q&A session with Dr. Hadjer next week, and the details of that session will be announced in ad. So I encourage you to think of questions as you're listening to the lecture and take notes. The last quiz will cover material from this lecture. So the focus of today's lecture is on hardware-aware neuroarchitecture search, which is a cutting-edge methodology that Dr. Hadjer has pioneered and has been actively developing to optimize the design of neural networks. And through her lecture, we'll delve into how this technique is revolutionizing the way we approach DNN design and automate the search for the most efficient and effective architectures. So let me briefly introduce Dr. Hadjer. Dr. Hadjer, she's a research scientist from IBM Research in Europe, in Zurich, in our Zurich lab. She is specializing in hardware-aware neuroarchitecture search for emerging AI accelerators, such as analog in-memory computing. She received her PhD from Université Polytechnique de Hauts-de-France in August 2023, following her master's and engineering degree in computer science from École Supérieure d'Informatique, Algiers, in Algeria. And her work on analog neuroarchitecture search has received the prestigious IEEE Open Source Science Award and the Best Paper Award at IEEE Services Computing 2023 Symposium. Her research focuses on making hardware-aware neuroarchitecture search more efficient, flexible, and practical. So it's a pleasure to have you, Hadjer, and back to you.
Hello everyone, I'm Hadjer Benmeziane, and it's a pleasure to give this guest lecture on efficient DNN design with neural architecture search. Thank you, Kautar, for inviting me. Deep learning models have traditionally been crafted with a single objective: to maximize the task-specific performance. And what I mean by task-specific performance is everything that relates to accuracy, F1 score, IOU, BLEU scores, etc. Just so we're not confused with the hardware efficiency. For instance, architectures like ResNet or VGG were designed to maximize the accuracy in image classification tasks. However, the landscape is rapidly evolving. The proliferation of edge devices and the staggering volumes of data that we have at the edge necessitates efficient architectures that can be deployed on our smartphone or resource-constrained devices. Authors of MobileNet, for example, created a model that is tailored for mobile devices with a small memory. If you check their version 1 and 2, you can see that they created it using handcrafted architectures and operators. Later, their version 3 used hardware-aware neural architecture search to develop it. And hardware-aware neural architecture search is the main topic of our lecture today. In this high-performance machine learning course, you have actually seen multiple optimization techniques. They take one network and then they try to shrink it. And what we're going to see during this lecture is that we're going to start by reviewing these optimization, and just so we understand where hardware-aware neural architecture search stands in this list. We will then introduce hardware-aware neural architecture search from an automatic machine learning perspective, or AutoML. And then we will delve deeper into the components of hardware-aware NAS, the search space, the search strategy, and the evaluation components. The last part of the lecture, we will go into a case study and we will apply hardware-aware neural architecture search to find the best architecture or deep learning model for analog in-memory computing, which is a novel hardware paradigm that we will introduce, of course. To do this, we're going to introduce a package called Analog AI NAS, and we're going to use directly this package that implements evolutionary algorithm to find the best architecture. Okay, so if we look at the landscape of deep learning optimizations, we can categorize these methods into three different categories. model compression, hardware-aware NAS, and code transformations. Specifically, model compressions are all the methods that tries to maximize the compression ratio, how much we can shrink the model, the accuracy, which is here a generic term for task-specific performance, and the hardware usability, which can be the energy efficiency, for example. Now, these methods work like this. Given a DNN model that is already pre-trained, we take this model, we shrink it, and then we get the compressed DNN model with the adjusted weight for it. And of course, this is hardware agnostic, regardless of the hardware that we are targeting, whether we are targeting a Raspberry Pi or a smartphone or a cluster of different hardwares, the compression is the same. And these methods can include something like quantization or pruning that you already have seen in this course. The next methods are the code transformations. Now, code transformations work specifically in the code implementation of the operation or the block or the DNN. So this tries to maximize the hardware usability, of course, and similar to model compression, this is already given a DNN or a block of operators that is already fixed with a set of weights that is already pre-trained. So given this DNN or block of operators, we try to do some transformations like loop unrolling, loop tiling, etc. to get to an optimized version of that code that can run in parallel in the targeted hardware. And of course, this is very hardware dependent and non-hardware agnostic, because we need to know how much parallelization we can have, how much cores we have in this processor, so that we can target as much, or so that we can allow as much parallelization as possible in our code transformations. And this is mainly done by the deep learning compilers such as XLA or Tiramisu, for example. The main method that will focus on in this lecture will be hardware-aware neural architecture search. Now, interestingly, hardware-aware neural architecture search is slightly different from the two methods in the sense that it's not given something that is already fixed with a pre-trained set of weights. No, it is given a set of different DNNs with a set of different operations. And we're looking at searching for the best architecture that maximizes accuracy and hardware usability. So given a set of DNNs that we call a search space, hardware-aware NAS technique will look into this set, trying to find the best one that maximizes accuracy and hardware usability. Now, these methods can be hardware dependent. So you can tell me I have a Raspberry Pi and I want the best architecture for this specific Raspberry Pi. Or we can say that we want something that is hardware agnostic and, okay, I have this set of different architectures, try to find the smallest in terms of number of parameters that also maximizes accuracy, for example, which makes it hardware agnostic. Okay, I've been using the term architecture, neural architecture search without actually defining the term architecture itself. So if you look at a deep neural network or a deep learning model, then we can represent it within this graph like this, where you have the inputs that goes through a series of different operations or layers, and then we have the output at the end. And each of these layers are actually connected differently. So if you look at a fully connected neural network, everything is connected with everything. If you look at convolution layers, for example, these are connected in sequence. We can have also some residual connections that connect some previous layers with the last layer, for example. So all of this, including which operation is executed by each of the layers, and including the hyperparameters like the kernel size or the stride, represent an architecture. So this is what we mean by defining the architecture or designing the architecture of a model. And you can see that we have a lot of different hyperparameters, a lot of different decisions to make so that we can define our best network. And of course, if you're a machine learning engineer, you're trying to find the best architecture for your task, you're not only gonna define your best architecture, but you're also gonna define which training hyperparameters you're gonna use for the learning rate, the momentum, the batch size, etc. So And then you need to know that accuracy and hardware efficiency are very sensitive to the architecture and the hyperparameters that we use in our model. So everything is really defined with the design of the architecture. So whether we design an architecture that is really good will define which hardware efficiency we're going to get at the end.
Now, to define hardware awareness from an automatic machine learning perspective, we start by understanding what is the machine learning workflow. And it's just a recall. I know that you know all of these, but the machine learning workflow will always start from data acquisition. We start by collecting the data. Then we need to clean that data. We need to remove the missing values, correct the types, etc. And then we need to prepare the data with the correct types, the correct format for the models. We do some feature engineering. We select the features. We create some new features based on the features that we had previous to the data preparation, etc. And then we select our model. If we have a tabular data, then we go for a machine learning type of algorithm like XGBoost, for example. If we had images, we go for a convolutional neural network or a vision transformer, etc. We select the model. And of course, if you understood hardware-aware neural architecture search or neural architecture search, then you understand that we're working at this cell here by selecting the model. Once the model is selected, we train it, we tune the hyperparameters, and we validate it on a set of unseen data, and then we deploy it. Now, of course, I removed all the backwards arrows, and there are a lot of backwards arrows. We can go back to cleaning the data, we can go back to feature engineering the features, we can go back to the model selection if you don't like the model, etc. In AutoML, we want everything to be done automatically without experts. So we want to allow non-machine learning experts to build and use machine learning systems for handling any task they want. So they just need to collect the data and then upload all the data into our system, and magically we can give them the model that will do the task that they need to do. And they just need to deploy it and that's it. So AutoML automatically do data cleaning, preparation, feature engineering, model selection, model training, and tuning and validation. So everything is done magically. And of course, it has a lot of different components or a lot of different methods. Not everything is done by just one method. And you can imagine that we have hyperparameter optimization to do the validation and tuning. We have automatic data augmentation to deal with process the data. And we have neural architecture search to basically find the architecture and find the best model that will do best the targeted task. And hardware-aware neural architecture search is just one component or one possibility of neural architecture search that includes hardware awareness. So if you do AutoML, of course, we are allowing non-expert to build machine learning system. We are reducing the cost of hyperparameter tuning by automatically trying different things and not just trying different things randomly and manually. We are allowing a machine learning expert to improve their model's accuracy by doing this huge tuning of a huge search space. And we are allowing machine learning experts to discover and find new architectures like MobileNet version 3. And we are also allowing these experts to find efficient architectures to be deployed in different hardware platforms using hardware-aware neural architecture search. And basically this last point is what we are dealing with in this talk. And we are dealing with creating new architectures, designing the architectures, and also designing architectures that are efficient using hardware-aware neural architecture search. Now, if you look at neural architecture search within this framework of AutoML, neural architecture search is the component that tries to automatically design deep neural networks. It is composed of three main components. You have the architecture search space. It defines all the set of different operations we're looking at, all the different set of DNNs that we are looking at so that we can find the best architecture within this set. So this is the architecture search space. We have the search algorithm. The search algorithm is an optimization strategy that basically look into this architecture search space and tries to find the best architecture within the search space. It can be reinforcement learning, it can be evolutionary algorithm, it can be gradient based, and we will see the definition of each one of them in few slides. And of course, to look for the best architecture, it needs some metric that says, okay, this one is better than this one. And this is where we call the evaluation methodology that comes to play so that it can give us the accuracy of the sampled model. So basically the search algorithm samples one architecture from the architecture search space. It gives it to the evaluation methodology, and the evaluation methodology will spit out the performance of that architecture A. And looping through the search algorithm, doing this multiple times, will give us basically the best model at the end. So this is the framework of neural architecture search. And as you see, as I already said at the beginning, DNNs are getting larger and larger. So current deep learning models are extremely complex and large. So we really need some kind of method that can get us closer to a model that is really accurate but really small at the same time, so that we can deploy it on edge devices and resource constrained devices. And this is where hardware-aware neural architecture search comes to play. So the goal of hardware-aware neural architecture search is to find the most efficient architecture for a target hardware and a specific task. Now, I'm going to decorticate this definition so that we understand it better. First, the term efficient is changing from NAS, where we were only looking at the accuracy or the task-specific performance. Now we are looking at two different things. We are looking at the task-specific performance, of course, the accuracy, the IOU, the average precision, etc. But we are also looking at the hardware efficiency. So how fast is the architecture? Is it deployable in these tiny memories? And is it energy efficient? So all of these becomes really important when it comes to hardware-aware neural architecture search. And we want to find this most efficient architecture for a target hardware. So we have different hardwares out there. So we have different hardware paradigms, different hardware devices out there, and we want to find the best architecture for a specific hardware. So you can see that over the years from 2018, the usage of neural architecture search have been diversified in terms of targeted hardware. So you can see that we are targeting GPUs, CPUs, FPGAs, ASICs, SoC, etc. Even some papers target multiple hardware at the same time, trying to find an architecture that gives an average good result on different hardware at the same time. Or there are also some specific methodologies that target no specific target, that are basically hardware agnostic, and tries to find the smallest architecture that is good in terms of the task-specific performance. And in terms of task, there have been also a diversity in terms of the targeted task in until 2023, with a different set of different neural networks that are targeting different tasks. So you can see that we have convolutional neural network, GANs, graph neural network, transformers, recurrent neural networks, and some specific variants of the convolutional neural network, with the capsule net, with the attention, with the extended convolutional neural network that include grouped convolution, depth-wise convolution, etc. So over the years, the concept of hardware-aware neural architecture search have been used into different set or different tasks and different targeted hardware. Now, if you look at the overview or the overall framework of hardware-aware neural architecture search, you can see that it changes from having only 3 components to having a multitude of different optional components, as well as the 3 main ones. So the 3 main ones are still the same. We still have the architecture search space, the search algorithm, and the evaluation methodology. Now, rather than evaluating only the task-specific performance or the accuracy, we're also evaluating the hardware efficiency with different methodology. And you can see that we actually have different optional components, like the fact that the architecture search space can be optimized by removing operations that we know are not good for the targeted hardware. An example of that can be, for example, the depth-wise separable convolutions are good for CPUs, but are not good for GPUs because of the lack of parallelization. So we would remove them if we're targeting GPUs, but we would keep them and remove the standard GPU for standard convolution, for example, if we're targeting CPUs. We can also have a hardware search space. So the hardware search space is basically for when we are targeting ASICs or when we're targeting FPGAs, when we can tweak also the tiling parameter, the number of processing elements, the templates of the ASIC, for example, can be also tweaked. And if we add the hardware search space, then the question would be, can you find the best architecture and the best hardware associated with it? And of course, at the end, when we find the best model, it's still the case that we can apply some additional optimization like quantization or pruning to the actual best model. However, it's not the best solution. The best solution is always to incorporate these quantization and pruning to the architecture search space, which means that we will have a convolution with 4 bits, with 8 bits, with 16 floating point quantization, for example, within our architecture search space. But it's still a possibility that when we get to the best model, we can also still quantize it and prune it. Okay, so now I'm going to go over each of the main components, the search space, the search strategy, and the evaluation methodology, and explain the detail types and the detailed methodology that is used to define, for example, the search space. Okay, so let's start with the search space. Intuitively, the search space can be defined with a layer-wise architecture space. What we mean by layer-wise architecture space is we define a list of predefined operations. So I can say that, okay, I have in my possible list of operators, I can have the standard convolution, the depth-wise convolution, the dense layer, and the ReLU. And then I can say, okay, I have the input here, I have the output here, and I can also set a predefined range of depths, which I'm gonna pick randomly. Let's say I have from a minimum of 8 to a maximum of 20 in terms of depth, in terms of layers, and then I'm gonna pick for each of the layer a possible operator from the predefined list. So this is the layer-wise architecture space. One question that you may have here at this point is whether or not the hyperparameter of each operator is included in the search, and it can be included when we include them in the predefined list. What I mean by this is when I have a standard conv, I will have a standard conv with 3x3 kernel size. I will have another standard conv with a 5x5 kernel size, and I would have another conv with a 7x7 kernel size, for example. And I do the same thing for the stride, for the padding, for all the different hyperparameters that I can manage or I can change within the network. Another methodology that comes from seeing manually created or manually crafted architectures like Inception version 2, for example, you can see that they have one cell or one block of different operators that is repeated all along the model. So you can see that this block, this Inception version 2 cell, is actually repeated all along. So one idea is actually to look for this cell and then just how many times I need to repeat it. So this is the cell-based architecture space, where rather than looking for the entire architecture, I'm going to fix the architecture and just look for these cells, what operators and how to connect them within these cells. And of course, I can define a predefined list of operators to create these cells. And one of the other things that I'm going to look for is the number of times this cell is repeated. So this is also within this cell-based search space. The last type of architecture search space is the super network. Now, the super network comes from the fact that if we define a cell base or if we define a layer-wise, then the network is extremely huge. Then I have a search space that is extremely huge. And one thing that I cannot do is I cannot train everything and basically train everything to get the accuracy of everything. This is impractical. That would be impossible. So one solution for that would be the super network. The super network idea is to define each layer with all the possible operators that can be in that layer, in that specific layer. So for example here, we're going to define a network where for each layer I can have a convolution 3 by 3, a convolution 1 by 1, and an average pooling. The advantage of using the super network is to use the weight sharing estimation methodology. What we mean by weight sharing is the fact that we can train this network once and then use all the subnetwork from, if you take a path from the input and then use, for example, a conv33 and then get to the output, this is one possible subnetwork within the super network. And then you can also take from the input, use the average pooling and get to the output. This, of course, we won't have a network that only includes an average pooling like this, but this is just for an example. If you go from an input and then go to the conv33 and then go to the output, this is one subnetwork. If you go from the input, go to conv11, go to the output, this is another subnetwork. And a subnetwork is one solution in your neural architecture search. So if you have this conv33 and if you train this whole super network as once, you will basically share the weights of this conv33 with all the subnetwork that uses it. And an example of this super network includes Dart or proxyless NAS, for example. Now, the main advantage of defining this super network like this, if you look at other strategies, the cell-based or the layer-wise, if you define a predefined list of operators that exceed maybe 20 or exceeds even 10, you have a huge search space that you cannot search for because you cannot estimate all the different accuracies of all the different architectures. But if you define a super network like this, you can go to, for example, proxyless NAS or Darts is about 10 to the power of 18. Proxyless NAS is something to the power of 10 to the power, it's 10 to the power of 19. So these are huge super networks and that you can train once and everything is trained at once and you just share the weights between all the different subnetwork to get to the validation accuracy. So this is an extremely gain of time when you do your neural architecture search. Okay, so these are the three different ways of defining a search space. You have a layer-wise search space, you have a cell-based search space, and you have the super network that allows you to do the weight sharing strategy. However, there are still some challenges in designing a search space, and one of the main challenges is the unavoidable human bias. As you can see, in each one of them, we have some kind of macro architectures that is defined. In the layer-wise search space, you have the fixed number of the fixed depth that you need to precise, and you need to define the predefined list of operations. So you are not allowed to do whatever operation, or you're not allowed to discover new operations, for example. In the cell-based search space, you have the macro architecture that is fixed. So you cannot play around with different architectures at the same time. The macro architecture is fixed. You're just trying to find the cell that is repeated all along. In the super network, you also have a fixed set of different operators that you can allow in each of the layers. So you will always go to some discovered operator and use it at this place. So, and this is unavoidable because it basically, at the same time, it restricts your search space, but at the same time, it makes neural architecture search practical and possible. We have also the fact that increasing the search space size, especially when adding hardware parameters, becomes extremely hard to search for. So especially when you add hardware parameters, when you decrease your possibilities of operators and then increase the depth, for example, you will have a lot of different complexities when you do the search. And currently, even if you see a wide range of different architectures that are looked for in 2024, for example, and I believe in 2023, and I believe in 2024 we have a wider range or a wider diversity of different architectures, but they are all clustered within the vision tasks. So whether it is segmentation, whether it is medical topics, whether it tasks, whether it is image classification, but they are all around vision tasks and not a lot in NLP or in speech. So this is one of the challenges of creating a search space and dealing with neural architecture search that are currently in use. Okay, now if you look at the search algorithm, hardware-aware NAS methods are always optimization strategies. And these optimizations are cast into either a single objective optimization, where you can use something like a two-stage method. As I said, the two-stage method is not it's not desirable, it's not the optimal strategy, where you search for the best architecture and then compress it. This is not the best strategy, but it's still in use. And in this kind of two-stage methods, of course, we want to maximize the task-specific performance, regardless of the hardware efficiency, because we know that at a later stage, we're going to compress it. We can also go for a constrained optimization, where we can say, I want to maximize my accuracy or my task-specific performance, subject to a certain constraint of the hardware. For example, it can say, subject to the fact that the latency of my architecture needs to be below this number, or the energy consumption needs to be below this number, or the flops, or the number of parameters, or the size of the model. All of this comes into the or is cast into a constrained optimization problem. On the other hand, we can also cast the hardware-aware NAS as a multi-objective optimization. And here we can either do scalarization, which is taking all the multi-objectives and turning them into one single objective with an aggregation function. And this can be, for example, a weighted sum of the accuracy and the latency, provided that we normalize them, of course. And we can maximize this, this objective. Another method which is actually better than the scalarization method in terms of trade-off. So we want to find the best architectures in terms of trade-off of accuracy and latency at the same time, is to go for the Pareto-aware methods, which are the pure multi-objective methods in optimization. And these methods do not define one objective, but they have multiple objectives at the same time, and they look at them simultaneously to find the best in terms of the trade-off. So I'm just going to give a bit more details on this, because it's really important to look at the Pareto-aware methods. So they actually define this Pareto front. So the Pareto front that you look at here are the set of solutions that are the best in terms of the trade-off between accuracy and latency. Sorry about here millisecond should be here and percentage should be here, of course. So we want to maximize the accuracy and we want to minimize the latency at the same time. But sometimes you can find architectures that are that are better. So for example, if you take these 2 points here, this point is better than this one in terms of accuracy, but this point is better than the other one in terms of latency. So if we want to maximize, if we want to find the best trade-off architectures, then we need to find the Pareto front like this one. And these points in green here are called the non-dominated solution, which means that no other solution is better than the other one. For example, if one is better than the other in one objective, then the other one is better than the other in the other objective. And the other blue points are the dominated solution, which means that one of the non-dominated solution is better than them. And we define this dominance by defining this operator, where we can say that if A dominates B, that means that for all the objectives, A is better than B or equal, and there exists at least one objective where A is strictly better than B. So this is the dominance criteria that is used to define the Pareto front. Now, as I said, there are different methodologies that are used in multi-objective or in classical neural architecture search. So we can define a reinforcement learning agent that basically go into the environment and construct the probability of selecting different criteria in the architecture. Like, for example, defining this agent here or the controller here that extract the number of filters, and then the filter height, the filter width, etc., the stride, etc., and then trains the architecture, this architecture that comes from this controller, and then getting the accuracy as a reward, and based on the reward, training the controller again, training the agent so that it adjusts itself, so that it gives us better architectures. This is of course, this is the simplest reinforcement learning agent. We can go ahead and define more more complex reinforcement learning agent with PPO, etc. One other strategy can be evolutionary algorithm, where we use a standard evolutionary algorithm to define our neural architecture search. So we can initialize the population, compute the fitness evaluation, so compute the initial objective for all of this population. Based on the fitness, we can basically select the top ranked architecture, and then we can use some evolutionary operation like some mutations or crossover, so that we create a larger population from the selected top ranked architecture. We then evaluate this new population, we create our next generation, and we iterate over this population updating phase until we are fine with the best with the results, or we get to a stop-in criteria. Usually we use a stop-in criteria where we say if you reach 100 iterations, or if you reach 200 iteration, you can stop there, and this is your last population. We rank the architectures within the last population, and we get to the best architecture. Of course, the evolutionary algorithm can be more diversified, or can be more complex than that, by choosing an initialization of algorithm that is, for example, Latin hypercube sampling, that samples architectures within the search space in a uniform way, so that we initialize our population better. We can also update the mutation and the crossover depending on the search space, or depending on how we define our architectures, whether we define it in a genomic way, so we can just use the crossover and the mutation that are used in classical genomic evolutionary algorithms, or we can use something that is more specific to what we are dealing with. We can say that, okay, for example, a mutation can be adding a layer to the model, another mutation can be removing a layer to the architecture, etc. Another strategy is the gradient-based algorithm. The gradient-based algorithm is defined with the super network strategy that we defined in the search space. So if we have a super network search space, we can define a gradient-based algorithm to search on top of it. A gradient-based algorithm basically searches and trains the super network at the same time, which gains a lot of time, a lot of search time, basically. So if you can see here, we're defining, here it's the DARTS model, or the DARTS strategy, differentiable architecture search. And what they are doing is they are superposing all the different operations together. So we can see from, if we go from tensor 0 to tensor 1, we can either apply a convolution 3x3, we can either apply a max Boolean or an identity, for example. And the task is to decide whether or not we should apply a convolution, a max Boolean, or an identity at this level, and the same thing for all the other connections between all the different tensors. So when we do the search, we're actually we're actually training the weights alpha, which are architecture weights that are optimized using gradient descent, just like we do with training the actual weights of the network. But these alpha are selecting criteria. So these alpha are selecting parameters. If you train them to say, this is the best operation at this level, and this is the convolution 3x3 is the best operation at the level of connecting 0 to 3, for example. And then once we basically train these alpha operation or alpha parameters, we just use, for example, a softmax or a discretization function just to get to the highest values of these architecture weights. And we can select, okay, for example, from 0 to 1, the highest alpha was given to max Boolean, so I can apply max Boolean at this level. From 0 to 3, the highest alpha was given to com33, so I can apply a com33 at this level. So basically, these are the gradient-based algorithms. So we add different architecture weights. These are associated with each operation that I want to apply at each level. And training them will give me which operation should I apply at this level. Similar to the search space, there are still a bunch of different challenges in the search exploration. Of course, the first challenge would be the computation cost and time of the search. That takes a lot of time and takes a lot of computational power. So dealing with a search strategy that explores better and exploits better the search space is the best thing. So it will basically reduce the search time. The increase in search space size, of course, can be significantly complex, hinders the search strategy. And also, if we go for multi-objective search strategies, they allow to find the optimal architecture in terms of trade-off, but it's still really complex to deal with and really complex to implement, especially if we go for a hybrid strategy between evolutionary and gradient, for example. And there's still the question between hardware-aware search space or hardware-aware search strategy. Should I include my hardware objective into the search strategy so that I can make it multi-objective? Or should I include it in my search space where I can define my search space knowing the hardware, so I can prune, for example, all the depth-wise separable operations for convolutions, for example. I can define ranges that are amenable to my hardware so that I can reduce it maximum. And then the search strategy, I can use whatever, knowing that every architecture in my search space are deployable in my hardware. So, and this is still a question that is in research, whether or not it's better to restrict the search space depending on the hardware, or choosing a multi-objective search strategy so that I can find the trade-off between the different objectives. And you can see that similar to the search space, actually we have seen diversity in terms of which solution or which strategy is used for neural architecture search. You can see now we have much more gradient-based solutions because we are leaning towards the super network strategy. Some of them uses Bayesian optimization that comes from the hyperparameter optimization, and we just use it as a hyperparameter, but for the architecture hyperparameter, not the training hyperparameter. And we have some other methodology that comes from optimization strategies, and these are very specific. Okay, so now we have seen the search space, we have seen the search strategy. The last component of hardware awareness is the evaluation component. I would say that the evaluation component is so the search space is the most important one because it defines all the ranges that we're going to get at the end. But the evaluation component is the bottleneck of hardware awareness because it will estimate the accuracy and the hardware efficiency, and depending on how it's estimated and how long it takes to estimate these values, we can say whether or not neural architecture search can be practical or not on the search space that we are given. So training one architecture on ImageNet, for example, requires around 2 hours on GPU A100. Running one architecture on a GPU to get the inference requires around 10 minutes. Maybe you can ask why basically this 10 minutes, this is huge, but basically deploying it and then running it for 100 of times to get the average latency. This is what is required. Will take around 10 minutes, and this is really prohibitive to neural architecture search. So if you look at early neural architecture search methods like NASNet, AmoebaNet, or MNASNet, these takes around 48,000 GPU hours, 75,000 GPU hours, or 40,000 GPU hours, which is around a month in terms of days. So it's too much to run, and if you increase the search space size, then you will take more than that, which is impractical if we want to use neural architecture search in a weekly basis, or for a given task, we want to get to the best architecture directly. So this renders basically this evaluation component. If we don't have an efficient evaluation component, it renders neural architecture search impractical. Okay, so as I said, full training is not possible. We cannot fully train the architectures that are sampled each time. So we need some kind of strategy that alleviates the training and do something that is really fast to estimate the accuracy of the models. One solution is doing partial training, like training for just 5 epochs and stopping there and saying that this is the accuracy that I'm going to use. Another solution is proxy dataset, where we use a data, for example, we use Cypher10 that is much smaller than ImageNet to search for architectures for ImageNet. And these are called proxy dataset, smaller dataset that can be used to search for architectures for the largest dataset. And then we have also learning curve extrapolation, which is practically the second solution, partial training. So we do partial training for a few epochs and then try to extrapolate the value after 100 epochs or after 200 epochs. And the last method is the surrogate models, where we basically train a bunch of different architectures. We create a data set where we have the architecture and their accuracies, and then we train a network that predicts the accuracies of unseen architectures from this data set. And this is called a surrogate model. So we have different methodologies, like the zero-shot methodologies that basically estimates using knowledge distillation, compares the feature maps of one network to the feature map of a teacher network that was trained. This is also one other solution that is used in neural architecture search, but not extensively used. The extensively used methods are the learning curve extrapolation and the surrogate model. In terms of evaluating the latency or the energy, similar things have been done. And for example, we cannot estimate or compute in real time the measurement of the latency. For some old methodologies, this is how it has been done, but it takes a lot of time. One of the strategies that we have is the lookup table. So basically creating a lookup table where you can see a convolution with 3 by 3 with this number of input channel would take this amount of time. A max pooling with this number of input channel and and this stride would take this amount of time, for example. And then basically when given a full DNN, I'm just going to sum the latencies of all the different operations in that DNN. And this methodology is called the lookup table. It has been used with FBNet and HotNAS, for example. Another methodology is the low fidelity estimation. However, it requires hardware experts to create this. Basically, we create analytical function. We can say that in this GPU, because I have this parallelization, because I can do this number of cores at the same time, or this number of operation at the same time, I can create an operation that can create a proxy or an approximation of the latency in this hardware. And this was used for FNAS, for FPGAs, or NAS caps for GPUs. Another methodology is to use these prediction models, and this is the same thing as a surrogate model that was trained to predict the accuracy, but here we train it to predict the latency. For example, proxyless NAS did that to predict the latency given different architectures, for example. one thing we did in our paper was to compare different strategies in NAS Bench 201, and you can see that different strategies gives different search time speed up. Of course, the real-time measurement is we compare against the real-time measurement. So real-time measurement is the slowest methodology. And then you have the lookup table that comes just after it, the analytical function, and then the surrogate model or the prediction model. And here for the prediction model, we used two different methods. We used XGBoost and we used MLP. And you can see that these methods are the fastest. But in terms of accuracy of the measurements, you can see that these methods are not the best compared to the lookup table or compared to the analytical estimation. Now, in terms of challenges of building an estimator, of course, there are different challenges and a lot of different challenges. First, we can see the scalability. When we grow, when the search space gets larger, it's getting really, the complexity of creating the estimator and getting an estimator that is correct is harder. We can also see that the generalization is really hard, either in terms of different hardware platforms. We cannot get one estimator that is good for different hardware platforms, and we cannot get one estimator that is good for different tasks and different types of architectures. We can also see the model complexity of the estimator itself. So the model complexity introduces some bias, introduces basically some bias. If you use an XGBoost, this is a tree-based architecture, so it introduces its own bias to the prediction. And if you use an MLP, for example, or if you use any other model, deep learning model, then you can extract some bias from the data set itself. And then we have some evaluation stability. So neural network training can be really sensitive to different factors like the random initialization, the hyperparameter, and the data variability. So if you are using a prediction model or a surrogate model, then this comes into play, and we need to make sure that the estimator is trained within different cross-validations so that we can make sure that the evaluation is stable enough. Okay, so now we are done with the part where we're talking about the hardware awareness. You have all the different components, the search space, the search strategy, and the search and the evaluation component. We understood each one of them and the types that we have in each one of them. Now we're going for the case study. In the case study, we're going to target a different hardware. So we're going to use neural architecture search to find the best architecture for analog in-memory computing. Now, analog in-memory computing, you may ask why analog in-memory computing? Analog in-memory computing is a promising hardware, especially that it significantly reduces the energy consumption by performing computation within the memory itself. So if you look at this cell here or this figure here, this represents a memory that can store all of these values. So in each of these resistance here, you can store one value here. And then doing vector matrix multiplication, like x multiplied by w that gives y here, is straightforward in these in-memory computing, because basically this input here, these input voltages will be equal to this x input. The values of the resistance here in the crossbar will be equal to the weights of the weight matrix. And then if we want to apply vector matrix multiplication, we will just apply these voltages here. And using Kirchhoff's law, we will get the current here that is equal to the y, that is equal to the result of vector matrix multiplication. So if we want to do vector matrix multiplication, this is straightforward. This doesn't change the memory itself. This gives us directly the result here. And why it significantly reduces the energy consumption? This is mainly because of reducing the data movement between memory and processor. In von Neumann architectures, you have the memory, you have the processor, and then you communicate everything with the processor via the bus. And this takes a lot of different energy that is consumed by the bus, basically. But if you reduce this data movement, you significantly reduce the energy consumption by the hardware. However, this has one significant disadvantage, and this is inherent to the characteristics of the analog itself. So this is inherent to the characteristics of this resistance that is here. And these are the noises and drift. So first of all, when you write something to this memory, you will have some noise. So what you write is not exactly what is written. And this is the noise that is inherent to the characteristics of the hardware. And then you have also the drift. The drift is the fact that the actual resistance value will change over time. So you won't have a fixed value over time. Not every time you read a value, you will get it the same. So you will have some drift. So the value of the resistance will change over time, will decrease over time, and this is basically detrimental to the accuracy of the model. So if you write some weights to this memory, after some time, and if you compute the accuracy at time step 0, and if you compute it again at time step 100, then you will see that your accuracy actually decreased because of this noise and this drift. So you're not only looking for architectures that are accurate, but we're actually looking for architectures that are resilient, that are robust to this noise. And also why analog NAS, so I'm just going to sum up here. Analog NAS, so because of this hardware is really good in terms of energy efficiency, but it's not good in terms of robustness and resilience to the noise. So we need, because it has some noise, inherent noise, so we need to find architectures that are really good. So analog NAS, neural architecture search with analog awareness, is really important because we cannot use the previous state-of-the-art models that are no longer resilient to the noise of the hardware. We need to find architectures that are resilient to the noise, that have a drop that is really small compared to the state-of-the-art models that will have an accuracy drop that is really high and takes benefit of this analog energy efficiency, analog energy efficiency. Okay, so to create a neural architecture search, as we said, we have 3 different components, so we need to set we need to choose a different type for each of the components. So for the architecture search space in analog NAS, we decided to go for a ResNet-like search space. I'm going to say why ResNet, but this is the choice that we have here. And then for the search algorithm, we're going to use an evolutionary algorithm. And for the evaluation methodology, we're going to train a surrogate model and we're going to use it directly. So the ResNet-like search space looks a bit like this, where we have the first convolution. We're looking for the output channel and the kernel size. And then we have a sequence of different main blocks. And inside each main block, we have a sequence of different residual blocks. And these residual blocks can apply different operations, can either apply a basic block or a bottleneck block. So why are we looking into ResNet-like search space? Because first of all of the state-of-the-art convnets that are out there, including EfficientNet, for example, have a ResNet-like macro architecture. So they look like a ResNet-like architecture, ResNet architecture. They are also able to tackle different tasks. They can tackle image classification, keyword spotting, or visual wake word. So we can, using a ResNet, we can just change the last layer and we can tackle different tasks, which is really, really suitable for what we want to do. And they are amenable for different analog hardware. So we can deploy them easily in analog hardware. For example, I can give you a depthwise separable convolution, for example, is not good for analog because it's really hard to deploy really small layers in these kind of memories. So we're going to waste a lot of space. Okay, so, and then one question that you need to ask yourself whenever you're creating your hardware NAS or whenever you're creating your search space is my search space diverse enough? So one thing that you can see, whether or not the search space includes already the state-of-the-art architectures that you have out there. So the search space, this search space, defining the search space like this, will include all the standard ResNets, will include the wide ResNet, the ResNext, and a different bunch of different state-of-the-art architecture. So if we didn't find any improvement above state-of-the-art architectures, we will at least find one state-of-the-art architectures within our search. And the size of the search space is 73 billion architectures that you can find in the package. So this is defined in the package, so you can take this 73 billion architecture and just look into it directly. So just to recall what is the basic block, what is the bottleneck block, and what is the wide basic block and the ResNext block, just to confirm that we can use all of these in our search space. So the basic block is just two convolution 3x3 in sequence with one residual block that connects the input to the output. A bottleneck block is a convolution 1x1 followed by convolution 3x3 followed by convolution 1x1 in sequence, and the same thing with a residual block from the input to the output. And when we say this is a wider basic block or a wider bottleneck block, we just mean that we increased the number of output channel of the convolution 3x3, like this. And a ResNext block actually includes different number of branches. So they include different, so it's the same bottleneck block, the 1-1, 3x3, 1-1. But it includes different branches that are added together. So rather than including one residual block with an empty skip connection, just an identity, it can include different bottleneck blocks in different branches. Now, when we talk about hardware awareness, so we defined the search space. We said, okay, we're going to go for the ResNet-like search space. We also need to define what are our objectives. Are we going for a multi-objective strategy? Are we going for a single objective? And if it's single, which objective are we talking about, etc. Because our analog hardware includes this drift, the drift of accuracy, so there is a drop of accuracy over time, then we cannot stick to the 1 second or the direct accuracy that we get after deploying the architecture. We need to wait a little bit and then take this accuracy so that we can take into account some kind of drift or some kind of resilience to that drift. So our main objective will be the 1-day accuracy, which is the accuracy that we calculate after 1 day of deploying the architecture, after 1 day of drift. We also include different objectives like the accuracy variation over 1 month, so the difference between 30 days accuracy and the 1 second accuracy. And we also include the 1 day accuracy standard deviation. So because we can, when we deploy an architecture and then we count, because it's noise, basically we apply in these analog hardware, we have some noise in them and we have some randomness. So we don't know what is the consistency of the actual performance that we are computing at this level. So we need to also be consistent. So we need to minimize the 1 day accuracy standard deviation so that we minimize or we maximize the consistency of having the same 1 day accuracy each time we compute that accuracy. Okay, so to sum up, we want to maximize the accuracy after 1 day of drift. We want to minimize the accuracy variation over 1 month to have robust architectures. And we want to minimize the 1 day accuracy standard deviation to have consistent performance computation. Okay, and the way we're going to do these, or the way we're going to evaluate our architectures when doing the search, we're going to actually create a surrogate model. As I said, a surrogate model is a prediction model that will predict the accuracies, that will predict whether or not our architectures are, architecture A is better than architecture B, or architecture B is better than architecture A. So to do that, we actually created a data set of different architectures. We created a data set of 1,230 architectures that were extensively trained. and then we trained them independently, and then we took 80% of this data set and we trained an XGBoost model to predict the one-day accuracy, the AVM, which is the accuracy variation over 1 month, and the standard deviation. To train the XGBoost to predict the one-day accuracy, we actually trained it to rank the architectures. So we actually trained it with the hinge loss, which is a ranking loss. The ranking loss, what it does, this is the formulation of this ranking loss, and what it does is it basically computes the difference between the predicted accuracy for architecture A and the predicted accuracy for architecture B, and tries to put them as far away as possible from each other so that the ranking is correct. And the AVM and the standard deviation were just trained with an XGBoost with a simple root mean squared error, so that we get to the closest as possible to the AVM of the ground truth and the standard deviation of the ground truth. Okay, so search space, we went for a ResNet-like search space. Evaluation method, we went for a surrogate model to predict the accuracies, or to predict the ranking, sorry. And then the search algorithm, we went for an evolutionary algorithm. Now this evolutionary algorithm have this overflow here. So we start by an initial population generation. We generate our population. We evaluate it using the pre-trained surrogate model. We validate that the average variation over 1 month is not above a certain threshold. We select the best architectures. We mutate some of the best architectures, and we create our new population. And then we iterate over some times so that we get the best architecture. The selection here, we choose the best performing individuals to move on to the next generation. And the mutation, we randomly perturb the architecture, and I'm going to give more details on the mutation. Okay, so the mutation, we actually have different blocks of mutation. We have the depth mutation, all transformations that basically change the depth of the network, whether it is adding or removing a main block, adding or removing a residual block, or modifying the convolution type from type A to type B. We have the width mutation. It can be adding or removing a branch, modifying the initial output channel here, or modifying the widening factor, which means widening the convolutions in the block. Or we have other mutations which are adding a residual connection, for example, or modifying this initial kernel size. Now the problem is formulated as follows. We want to maximize the accuracy over the standard deviation, because we want to maximize the one-day accuracy, but we want to minimize the standard deviation of the one-day accuracy, subject to some constraint. We want to, first constraint is the AVM, the average variation over one mount. We want it to be below a certain threshold. So we want architectures that are robust. And we want the number of parameters threshold to be below a certain threshold. The number of parameters of the architecture to be below a certain threshold. We added this constraint to find different architectures at different thresholds. And of course, the selection method is a tournament, which means that we are selecting the top architectures, the top ranked architectures each time. And these are just hyperparameters of the evolutionary algorithm, like the number of iterations is set to 200, the time limit is set to 100, and the population size is set to 100. And these are the different mutation probabilities and the selection. When you run this analog NAS, if you give it plenty of time of 20 minutes, for example, you can reach a maximum architecture accuracy of above 95%, which is above state-of-the-art architectures for Cipher 10, for example. And these are run for Cipher 10 with edge models around 1 million parameters, or tiny models which are around 300K parameters, or even less than 100K parameters. So you can see that the reddish lines are always our models, the models that we find, against the model that are state-of-the-art, which are the blue lines. You can see that the red lines are always on top of the blue lines, regardless of whether we are looking at tiny models or edge models. And our best model is around 860K parameters, which is above wide ResNet, which is 26 million parameters. So if you compare like below 1 million to the 26 million parameters, you can see that our model is much more robust. And now in terms of architectures, what we have seen is that state-of-the-art architectures are much deeper, and our networks are wider and much shallower than the state-of-the-art networks. So now we can go over to the notebook and explore the notebook to extract ourselves some architectures that are good for Cipher 10.